Welcome to our video on row reduction and echelon forms. In linear algebra, row reduction is a powerful technique for solving systems of linear equations and performing matrix calculations. By the end of this video, you'll understand the step-by-step process of row reduction and the different types of echelon forms. Let's start by understanding the three elementary row operations that are used in row reduction. The first operation is swapping two rows. The second operation is multiplying a row by a non-zero scalar. And the third operation is adding a scalar multiple of one row to another row. These operations are powerful because they allow us to transform a matrix without changing the solution set of the corresponding system of equations. Now, let's define what we mean by row echelon form, or REF. A matrix is in row echelon form if it satisfies the following conditions. First, all non-zero rows are above any zero rows. Second, the leading entry, which we call a pivot, of each non-zero row is 1. Third, each pivot is to the right of the pivot in the row above it. This creates a staircase pattern of pivots from top left to bottom right. Building on the row echelon form, we have the reduced row echelon form, or RREF. A matrix is in reduced row echelon form if it satisfies all the conditions of row echelon form. And additionally, each pivot is the only non-zero entry in its column. This means that all entries above and below each pivot must be 0. Let's look at an example to see the difference between REF and RREF. Now, let's discuss the process of Gaussian elimination, which is the algorithm we use to transform a matrix into row echelon form. Here's the general strategy. We start with the first column and first row. If needed, we use row swapping to bring a non-zero entry to the pivot position. We scale that row so the pivot becomes 1. Then we use row addition to zero out all entries below the pivot. We move to the next row and column, and repeat until all pivots are placed. To reach reduced row echelon form, we then go backwards and clear entries above each pivot. Let's work through our first example, converting a 3 by 3 matrix to row echelon form. We'll start with the matrix A, which has entries 2 for -2 in the first row, -1, 1, 5 in the second row, and 3, -2 for in the third row. Our first step is to create a pivot of 1 in the top left position. We divide the first row by 2, giving us 1, 2, -1 in the first row, with the rest unchanged. Next, we need to zero out the entries below our first pivot. We add row 1 to row 2 and subtract 3 times row 1 from row 3. This gives us zeros in the first column below our pivot, with the remaining entries adjusted accordingly. Now, we move to the second row, second column. We need to make this a pivot of 1, so we divide row 2 by 3, which is the current value at that position. Finally, we zero out the entry below our second pivot by adding 8 times row 2 to row 3. The result is our matrix in row echelon form. To convert our matrix to reduced row echelon form, we would continue with a few more steps. First, we would scale the third row to make the pivot 1 by dividing by 35 thirds. Then, we would clear above each pivot, starting from the bottom right, and working our way up. This would eventually give us the identity matrix, which is the reduced row echelon form of our original matrix. Now, let's look at our second example, where we'll convert an augmented matrix to reduced row echelon form to solve a system of linear equations. We start with an augmented matrix representing a system of 3 equations with 3 unknowns. The first pivot is already 1, so we can directly zero out the entries below it. We subtract 2 times row 1 from row 2 and add row 1 to row 3. Next, we see that the pivot in row 2, column 2, is already 1. We'll zero out entries below and above this pivot. We subtract row 2 from row 3, and we subtract 2 times row 2 from row 1. For our third pivot in row 3, column 3, we have -1, so we need to scale row 3 by -1 to make it 1. Finally, we clear all entries above our third pivot. We add 5 times row 3 to row 1, and subtract 2 times row 3 from row 2. Row reduction and echelon forms are fundamental tools in linear algebra with many applications. They allow us to solve systems of linear equations. They can be used to find the rank of a matrix, which tells us about the number of linearly independent rows or columns. They help in computing the inverse of a matrix, and they're useful for determining if a set of vectors is linearly independent. In summary, row reduction transforms a matrix to echelon form through a series of elementary row operations. Row echelon form has pivots arranged in a staircase pattern, while reduced row echelon form additionally ensures each pivot is the only non-zero entry in its column. These forms reveal the structure of linear systems and provide direct access to their solutions.